Okay, so we learned about Hooke's law, which is about springs stretching, right? The stretch here is our x. We have a spring coefficient k that depends on the spring itself. And then we have the downward force with which we're pulling the spring. That's a review of Hooke's law, just really briefly. Today, we're going to talk about something a little bit different. And we're going to talk about tension. We talk about tension in terms of T. A capital T means tension. And when we talk about tension, we're talking about a force exerted by a string, a rope, or wire that is pulled tight. Tension essentially is when you are pulling on an object. So if this is my object and I'm pulling on it this way with a string or a rope or a wire, there's tension. Similarly, if I have a rope and it's being pulled on both sides, there's tension occurring. And this rope is tensile. A tensile force is tension. Tension and tensile mean the same thing. So in an ideal string, no matter where you are on the string, you're experiencing tension in either direction. So if I were to zoom in on this portion of the string, the tension or the pull would be the same even if I moved this box to the left or to the right. The tension along the entire rope is going to be the same. So we're going to start using tension in some of our free body diagrams as well. We also need to think about another concept called equilibrium. You should probably already know the word equilibrium from other science classes, but equilibrium means equal. When something is equal, this time we're talking about net force being equal or forces all being equal. If I have equal forces acting on all of my objects, my net force has to be equal to 0, right? If my net force is equal to 0, there is something about that object that can also be true. If my net force is equal to 0, if we're thinking about Newton's second law, force equals mass times acceleration. If this is net force, 0 equals some kind of mass times acceleration. We know that our mass is a non-zero number. So in order for this statement to be true, that means that our acceleration also has to be 0. So something in equilibrium, an object in equilibrium, has a net force of 0, which also means that acceleration is equal to 0. Just because acceleration is equal to 0 does not mean that our velocity equals 0. It simply means that our velocity is not changing. So it does mean that velocity is constant. That's equilibrium. Our net force, or the sum of our forces in all directions, is equal to 0. This is just another way of writing net force. So now we're going to walk through a couple examples to help us understand things like tension and equilibrium. The perks of doing this in the morning. Love school announcements. All right. So our problem. A person hoists a bucket of water from a well and holds the rope, keeping the bucket at rest. All right, simple enough. A short time later, the person ties the rope to the bucket's handle. This allows the rope to hold the bucket. Is the tension in the rope greater when they hold the rope or when the rope is tied? Go ahead and pause the video and see if you can draw a picture of these two cases. All right, so now that you have given it a try, I'm going to go ahead and draw the picture. This one might have been a little bit more difficult to visualize because now we're starting to use things called pulley systems. So maybe this is my well. Let's see, a lot of times they have like the little covers on the top and on the sides. They've got little pulley things, and then they've got a pulley up top. And this is my bucket. And this is my rope that my person is holding. Okay, so this is case one with a person holding the rope. Otherwise, we have case two. So I still have my well. But this time, with my bucket, they've tied the rope back to the bucket. It'd probably be a little bit more centered than this, but that's the same idea. So now we have to think about the tension in the rope for each of these scenarios. So I'm going to erase this. You can keep it in your notes, but I'm just going to allow us to keep the word problem and zoom in on the buckets a little bit better. So with bucket one, it's coming up over a pulley and being pulled this way, right? With bucket two, or case two, this is more what it looks like. We have the rope attached to itself on both points versus we have one point of attachment here. So what do we know about the forces happening on each of these? Hopefully you understand that each bucket has some sort of mass, m. We're going to assume that m is the same for both buckets, right? And we also need to understand that we have some force acting downward on the bucket. What force would that be? That force would be weight for both of them. Weight is going to be equal to mass times gravity, right? Since we don't know the mass, then we can't really solve for it. So I'm just going to write mg. Now we have to think about the other force that's acting on each of these buckets. We're going to start with case 1. We have one point of contact with the rope, so there has to be some sort of tension force here. We know that this bucket is not moving, right? The person is holding it still. So what can we assume about these two forces? If it's being held still, we know that the sum of forces in all directions is equal to 0. The sum of our forces in this case equals T minus W. We can then take this part of the equation, right? 0 equals T minus W, and rearrange it. We technically know what W is. So we could say that T equals W. So tension in that rope is equal to mass times gravity. Now let's think about the second case. We have the weight of the bucket holding it down. Now we have to think about the other forces acting on the bucket. But hey, we have 2 points of contact here, which means that we're going to have 2 forces here. Since it's a pulley system, this rope is going to be equal on both sides. So we have tension along the whole rope, right? We discussed that along a rope, when there's tension, tension should be equal across the whole rope. Well, when we do that, we know that the sum of our forces has to equal 0 because the bucket is in equilibrium. And our positive forces, we have 2 T's in the upward direction minus W. Again, like we just did, we can take this part of the equation and rearrange it and start searching for T, what our tension is, right? Because we're looking at, is the tension greater when they hold the rope or when the rope is tied? So I have 2T equals W. I can take this 2 and move it to the other side, which means that T equals W divided by 2. And finally, I can sub out my W for mg. T equals mg divided by 2. Or if I really wanted to, I could rewrite this as 1/2 mg. To finish this problem, we need to look at these two values, the tension in the first case, the tension in the second case. Which one do you think is greater? Well, my brain tells me that if I have a value here and the same value here, in the first case, I have that value. In the second case, I have half of that value. So where is the tension greater? Tension is greater when the rope is held. Okay, we're going to do one more problem with equilibrium and tension to make sure that we really understand this. So we have a 1.84 kilogram bag of clothespins. Hangs in the middle of a clothesline. Causing the clothesline or causing it to sag at an angle theta equals 3.5 degrees. Find the tension force T in each part of the clothesline. All right, so now we have to do a little bit of trig as well. What we're trying to do is find the tension in each part of the clothesline. What do we know about tension? It's the same across everything. So even though it sounds like we're trying to find a bunch of things, we're just trying to find tension. Tension is going to be the force. So let's go ahead and draw this out. I'm going to get you started on the drawing. So I have my two clothesline posts. Now draw the clothesline with the bag hanging in the middle. All right, so my clothesline with the bag hanging in the middle, I know it's going to sag.
Bun, green beans, and mixed fruit. Breakfast tomorrow is scrambled eggs, toast, fruit, and juice. Please stand for the pledge. Well, if you need a retake taken today and you haven't done so yet, please make your way to the gym for your retakes. Thanks.
I was not banking on the announcements this morning. I need to be more mindful of that when I decide to record. Okay, so I have my clothesline posts, I have my clothesline, and then we have a bag of clothespins sitting in the middle, causing it to sag. And it says it sags at an angle of 3.5 degrees. So I'm going to say my angle here on either side, right, is theta. And we know that theta is 3.5 degrees. So I'm just going to leave it as theta. So now I have to establish a coordinate system. I have an X in this direction and a Y in this direction. Okay. Now what do you think we have to do next? Hopefully you're thinking, we probably need to split the force up into an X component and a Y component. You would be right. Because tension is going to be, let me do this in a different color. Tension is going to be running along the clothesline like this. And you can tell it's running at an angle. That angle is 3.5 degrees. So now we have to figure, well, how much of that tension is going to be in the Y direction, and how much tension is going to be in the X direction. So I'm going to draw my full triangle out here. I know I have So I know I have my tension going in this direction. We're just going to focus on the right side here of my drawing because we know that the tension's going to be the same no matter what, wherever we are. And we know that this angle is 3.5 degrees. So we're going to have some sort of tension in the y direction plus some sort of tension in the x direction. In order to split these up, hopefully you remember that when we're going to find the y of something, it's going to be the sine. So my tension in the y direction is going to be equal to my tension times sine of theta. Okay, we could also figure it out by saying, okay, if we know, let's pretend we know t, right? T is what we know or what we're trying to find, but we have to split it up so our unknowns are ty and tx. And we're going to be working in terms of variables. So we're not going to have numbers, but if we remember SOHCAHTOA, it's some old horse came a-hoppin' through our alley, or SOHCAHTOA. All right, so if I'm looking for ty, that's my opposite, right? It's opposite of my 3.5 degrees. So to find ty, I'm going to choose sine because it has opposite. And then we're going to pretend that we know our hypotenuse. So how we got to this ty sine theta is I said that sine of theta equals ty divided by t. And then I multiplied both sides by t to get t sine theta equals t sub y. Okay, that's how we hopped from this triangle to this. We can do the same thing with our x, right? So we can say, okay, I'm looking for t sub x. That's my adjacent. If I want it in terms of t, I'm going to have my adjacent over my hypotenuse, which is going to be cosine. So then I could do cosine theta equals t sub x divided by t. I could multiply both sides by t, and that would end up giving me t in the x direction is equal to t cosine theta. In the x direction, though, if we really think about it, we only have tension in the x direction, right? So we have t sub x acting this way and t sub x acting that way. So t sub x in this case isn't really going to be helpful. But in the y direction, we have the weight, and then we have two tensions that are pulling up at angles. So if we split this into just the y, we have the weight straight down, and then we have the y components of both of those, which would be our t sub y's. So let's start summing up our forces in x or in the y direction. Sum of forces in the y direction is equal to T sub y plus T sub y minus W. The y component of the T, and we have two of them. And then we have the W. So now what we're going to do is just start subbing things out. See if you can finish solving this on your own. Pause it, try it, and then I'm going to solve it, restart the video, and then we'll solve it together. So the forces in my y direction, I'm going to start combining these things a little bit. So I'm going to say I have two.
Could I have Adley do Elena's balance to the gym, please?
2t sub y's minus w. This is also equal to, we said t sub y in terms of tension, because eventually we want just the t, right? We don't want t sub y, we want our full tension. So I'm going to say it's 2t sine theta minus w. Hey, we can quantify our w. So now we have 2t sine 3.5, right, degrees. I'm going to start plugging things in. Minus mg, that's equal to 2t sine 3.5 degrees minus, what is my mass? 1.84 kilograms. Times 9.81. It's not a negative 9.81 because I already accounted for that negative when I put my subtraction on here. I already accounted for the direction when I said my W is negative. Okay. Now we can start condensing terms. Just going to fill this in here. So the sum of forces in my y direction is equal to 2t sine theta, which I'm going to pull out my handy dandy calculator. The sine of 3.5 degrees is 0.061. When I multiply that by 2, I get 0.122 t. So I condensed my 2 and my sine of 3.5 minus, and then we have 1.84 times 9.81 is 18.0504. Okay, but now I'm dealing with this sum of forces in the y direction. I kind of want to get rid of that. But hey, remember, this is an equilibrium. Nothing is moving. So I can replace this sum of forces in the y direction with 0. 0 equals 0.122t minus 18.0504. Now I can start rearranging things. The first thing I want to do is I say I have subtraction, and I need to undo that first. So I'm going to add 18.0504 to both sides. Now I can undo the multiplication of 0.122t by dividing both sides by 0.122. And when we take 18.0504 divided by 0.122, we get 148 newtons, or 148 equals T. And again, you have to think, okay, tension's a force. What is my force going to be in units of? Making sure that my base units are all okay, but I have kilograms. And then my G is going to be meters per second squared. So all of those base units are right. So I'm going to have newtons. 148 newtons is our tension. Okay. We're going to do one more problem. This one should be a little bit faster.
Could I have Brianna Gabriel? Could you send me Brianna Gabriel to the gym?
We got lots of announcements today. All right. So now we're going to start trying to do a free body diagram. So in this example, a 9.3 kilogram child sits in a 3.7 kilogram chair. Her feet do not touch the ground. So in this case, are we talking about tension? No, we're not talking about tension because we don't have a rope or a wire or anything like that pulling. We don't have any pulling forces. So this is just a practice problem on how to draw a free body diagram. So the first free body diagram that we're going to draw, FBD, free body diagram, for the child. Start with your dot, okay? That's going to be your child. Try to draw your free body diagram. Pause the video. Okay, so hopefully you paused it, hopefully you tried. So if I have a kid sitting in a chair, if she's sitting, there's going to be some sort of weight, right? Which is equal to mass times gravity. We know her mass is 9.3 times 9.81. Again, it's not negative because we're already giving it that negative by saying it's a downward force. 9.3 times 9.81. It's going to be 91 newtons. 91 because sig figs, I have 2 sig figs, so my answer also needs to be 2 sig figs. So then we know she's not falling. And if we just had a downward force, we know that she would have to be accelerating at a speed that is her force, this force divided by her mass, but she's not falling. She's sitting on a chair. If she's sitting on a chair, she's not moving. That means that she's in equilibrium, which then tells us that the sum of our forces is equal to 0. So we have to then balance out this force with the normal force of the chair pulling up on her. If she's in equilibrium, we know that it has to be equal and opposite to her weight. So we know that also has to be 91 newtons. All right. So now draw a free body diagram for the chair. Again, start with a dot. Try drawing out all of the forces that you can think about acting on the chair. Pause the video, try your best. All right, so we have some sort of weight going downwards. And there's 2 different ways that we can think about this. Both give us the same answer. The first way I'm going to think about it is that this is just the weight of the chair. which is equal to the chair's mass times gravity, which is equal to 3.7 times 9.81. Which is 36 newtons. And then we know that there has to be some sort of normal force that's equal and opposite to that on pushing up on it to make the sum of our forces equal 0, because again, it's an equilibrium. It's not going anywhere. That's the chair if it were by itself. But is the chair by itself? No, it's not. So we also have to account for the weight of the child. We also have the weight of the kid. I'm going to do WK. So these would be WC and normal C, weight of the chair and the normal force of the chair. And we already figured out that's 91 newtons. And then we have what would have to be the normal force to counteract the kid, which is another 91 newtons. That's one way that you could think about it. The other way to think about it is I have a weight. I know my combined weight is going to be of the child and the chair, right? That's the total weight of that system. So instead of thinking about the child and the chair separately, I'm thinking of them together. So the weight of the child and the chair is going to be 9.3 plus 3.7, which is 13. That's the mass times 9.81. So that gives me a total weight of 128 newtons. And again, my net force has to be equal to 0. So I have some sort of normal force that's equal and opposite, which means it's 128 newtons. We know from the problem that there's not going to be any sort of forces in the x direction. If you add 91 and 36, it gives you 127. We're 1 newton off because of a rounding error. These are both the same solution.